So the first thing here that we're going to look at is kind of a review of function notation, except for a little bit different than what you're used to. Like function notation, you're given an f of x function, you're asked to find f of 3. Normally you just plug in 3. You definitely have done function notation where you've had to plug in maybe like x plus 3. Like f of x plus 3, so you actually plug in the x plus 3. This is a little bit different, and it does have some meaning behind it. There is a reason we do it. But in this particular case, we're evaluating f of x plus h. So essentially just like if it was an f of 3, wherever there's an x, you would put a 3. Well, wherever there's an x here, we're going to put an x plus h. So f of x plus h equals 2 times x plus h squared minus x plus h. Now, always remember, if you're substituting in a polynomial with more than one term, you have to lock it up in parentheses so you distribute the negative. And then plus 3. And then we're just going to simplify this. So when I square out the binomial, and again, I have a 2 that ends up needing to be multiplied by all of this, so I need to keep this squared portion locked up in parentheses. It's going to give me x squared plus 2xh plus h squared. And now I can distribute the minus, so minus x minus h, and then plus the 3. I'm going to distribute that 2 now, 2x squared plus 4xh plus 2h squared minus x minus h plus 3. It's just a process. Be patient through it. And then I don't believe I can combine any terms, can I? So that's it. Now, I'm going to use what I just found to bring me to b. And this expression you are going to have to memorize. We'll just focus on the algebra right now, and then we'll come back for a minute and I'll talk about what does all of this mean. So f of x plus h, which we already did, I'm just going to pull from over here. So that's going to be the right small because it's obviously long. There's my f of x plus h. Minus f of x. Now, again, f of x was given to us. It's a trinomial. It's this 2x squared minus x plus 3. So keep it locked up in parentheses.
Pardon the interruption one more time. Juniors and seniors who have a study hall this period, you're invited down to the cafeteria to visit with the colleges. We do have about 20 colleges in the cafeteria this morning right now, 10 to 10:30. For any students who want to come and have a discussion with them about the program.
What's that? Oh, sure.
Study hall this period, cafeteria.
There you go. So from here, I just need to distribute my negative and sort of combine like terms. I'm going to do all that at once. So I have a 2x squared, and then I'm going to subtract a 2x squared. So that's actually going to be a wash. You're welcome. I have a 4xh, and I don't have any other xh terms, so I'm just going to bring that down. I have a 2h squared, and I don't have any other h squared terms, so I'm just going to keep that plus 2h squared. I have a minus x, and then minus a negative x over here. So minus x, is, and then plus x is what's going to happen when that negative gets distributed. Are you with me? Minus x plus x is actually going to cancel. I have a minus h, which has nothing else up top to be combined with. And then I have a plus 3 minus a plus 3, which is gone. 3 minus 3. All over h. And I can still evaluate y. I can still keep going. Simplifying. What could I do, Olivia? Right. So if you want to show yourself factoring out like a GCF of h, you can do that, or you can just kind of knock a degree of h off of each one of those terms. So that'll be gone, one of those h's will be gone, and that'll be gone. But I use the term gone on the last term loosely. I'm dividing an h out, and h divided by h is not 0, correct? It's 1. So I'm left with 4x plus 2h minus 1. And that's my evaluation, okay? So f of x plus h minus f of x all over h is something you're going to have to memorize. It is called the difference quotient, okay? I write that down below, right here. So if you want to circle it and write difference quotient. So if you ever just see blindly what is the difference quotient on a given function, you have to know that that's what you're doing. You're doing f of x plus h minus f of x all over h, and you're going to simplify it out. Okay, now, here's what it is. In calculus, for the first time, you're going to start to explore slope on functions other than lines. Linear slopes are real easy. Rise over run, and whatever that slope is, it's the same on the entire line, right? That's what makes something a line. It has a constant slope. It's a straight line because it's changing by whatever that degree is all the time. Parabolas, polynomials in general, radical functions, log functions, all of these other types of functions have a curve to them. And if they have a curve to them, that means that their slope is always changing. Do you follow? So obviously here we have a pretty steep negative slope and still a negative slope, but it's starting to become less steep. As we approach the vertex or the turnaround point, what's the slope there, do you think? I saw you mouth it. Yes, she's correct. That's a slope of 0 because it's for that moment, it's neither increasing nor decreasing, right? Decreasing equates to a negative slope. Increasing equates to a positive slope. So we're going to start to figure out what is the slope on our curve. And keep in mind, your slope on the curve over here is much different than the slope on your curve down here. The slope is always changing, okay? It's really, even at two sort of consecutive points, your slope is going to be different from one to the other. So the idea here, and let's say we're trying to find the slope at x. We all know that the slope formula is essentially y2 minus y1 over x2 minus x1, correct? That's your slope formula for a line, or the slope between 2 points. So the idea here, and the reason this difference quotient comes up, is because, and let me kind of get up here, and I wish I had an animation thing. I thought I had a pencil or a ruler. I don't think I did. Oh, yes, I do. 1 second. Okay. So if we're trying to find the slope right here at x comma f of x, that's just xy. Are you with me? We're just using f of x for y because it's what we do with adult math. So if we're trying to find the slope instantaneously at that point, we're going to start with some arbitrary point over here, random other point on the curve that's several units away, right? 8 units to be exact. If this has an x-coordinate of x, they're calling this other point an x-coordinate of x plus h. Are you with me? So the y-coordinate on this one is f of x, right there. And the y-coordinate on this one is f of its x-coordinate, which was x plus h. You follow that? So I have the points labeled x, f of x, and x plus h, comma, f of x plus h. Now if I am to connect these 2 points with a straight edge, is that the same slope as the slope is, or the degree of increasing is at the point? Would you say this is a steeper slope or a less steep slope than the slope right at that point? Steeper, right? Okay? So how can we get the slope of, does anyone know what kind of line that's called? Secant line? Are we okay with that? There's secants in circles where it hits the circle twice. This is a secant line, it's hitting the curve twice. What we're going to do is we're going to kind of slide this secondary point closer. Okay, so let's say we move it down here, and there's my original point. And now if I connect those 2 points, it's still going to be a secant line. But I think we can all agree that the slope of that blue secant line is getting closer to what the slope is instantaneously at that point. Do we follow? So the closer we pinch these points, and by the way, I'm using 2 points because we can only calculate the slope when we have 2 points, correct? So I sort of have to stick with a secant line. You with me? Because I need 2 points. But the ideal thing that's going to happen is that those points are going to get infinitely close together. Essentially, h is going to get closer and closer to 0. So right now, let's pretend h was 2, so these were 2 units apart. Well, now when I slide x plus h down, now h might only be a half of a unit. And I want h to get closer and closer to 0 so that those points are essentially on top of each other. Do you follow? You with me? Okay? So what I'm going to do from here is, back on the paper, I'm going to essentially find the slope of the secant line using those generic coordinates. So the slope of the secant line is going to be the y-coordinate minus the y-coordinate. That's going to be f of x plus h minus f of x over the x-coordinate minus the x-coordinate. So x plus h minus x. And so when we simplify that, we don't have a function to plug into, so I'm just going to leave the numerator f of x plus h minus f of x. But on the denominator, x plus h minus x is just h, right? And there's your difference quotient. What the difference quotient is really the slope of a secant line. So I'm going to write difference quotient right there. And this is really one of the introductory ideas of calculus. It's going to seem a little funny because we're doing this here, and then we'll move on in the chapter, and we really won't hear much about it until we start calculus, and then we'll be doing a lot more with this. But for right now, that's where the difference quotient comes from. It gives you the slope of the secant line. And ideally, when those 2 points pinch closer and closer together, the secant line, I'm going to put them almost on top of each other, the secant line essentially turns into what kind of line? Tangent line, exactly. As those points get closer and closer to each other, so they're only off by, let's say h is like 1/1,000,000th of a unit. So essentially those points are on top of each other. That secant line now looks like it's the tangent line. And whatever the slope of that tangent line is at that point is going to be the slope of the curve at that point. So we'll look at, when we get there, what happens to the difference quotient as h gets closer and closer to 0. Why can't h be 0 right here? Why couldn't I just set h equal to 0?
Because it'd be undefined.
Exactly, because it would be undefined and we would have no numerical value of the slope. So what we'll see happen is that h in the denominator will kind of work itself out, and then we will be able to assume h is 0. Okay? All right. Switching gears. Piecewise functions. Did you do these last year? I believe you did. Okay? So this particular piecewise function has a meaning and a context attached to it. it's referring to a cell phone plan where C of T is the cost dependent upon T, the number of minutes that you're on the phone. So if C of T equals 20, if T is between 0 and 60, who can interpret for me what that means? What does that mean relative to the cell phone plan and the cost and the minutes? Trista, can you give it a shot?
If you're on the, am I evaluating A?
No, I asked you an offbeat question.
Basically, like, T determines your cost.
Right, but like, so what does this mean for someone who's paying their cell phone bill?
I think I left my textbook in here over the weekend.
Where would you?
Or if I either borrow one or
Yeah. Where would you have left it?
either over there
Or back on the shelf?
or yeah.
Okay, sure, go ahead. So if you're paying for a cell phone, what does that first line of that piecewise function tell you?
If your number of minutes is between 0 and 60, your cost is 20.
Right. So if you're on the phone for 0 minutes, as long as you've signed up for this plan, right? Whether you're on the phone for 0 minutes or 60 minutes, you're going to pay $20. Okay? And then the second piece tells you what happens if you're on the phone for over 60 minutes, which is what? How do you interpret that, Andrew?
It's like 40 cents extra per minute.
Perfect. Yep. So they they add on 40 cents for every minute over 60. For example, if it was 62 minutes, 62 minus 60 would give you 2 minutes at 40 cents each, plus the initial 20. Does that make sense? So that's what it means. So if we evaluate C of 30, that's just, you got to figure out anytime you're evaluating piecewise, which piece are you using? If the time is 30, you're using the first piece because it falls in that interval. And if you evaluate that, Nate, what does C of 30 equal? So we're essentially looking at that top equation. If T is 30, what's your cost? 20, right. If T is not involved in the equation, then truthfully, T doesn't really matter on that one, and you're paying 20 regardless. Good. C of 100, obviously that falls into the second piece because that's over 60. So you're going to do 100 minus 60, which is 40 minutes. Again, we have no calculator. What's 40 minutes times 40 cents? Think logically about it as well as thinking about taking mathematical shortcuts like 40 times 0.4. Think about your 4 times 4 is what? 16. Now what happens with the decimals? Think logically about it. 40 cents per minute. So 40 cents per 40 minutes for each of those 40 minutes. If it was 50 cents a minute, how much would 40 cost? If it was 50 cents a minute, how much would you pay for 40 minutes? Oh boy. Okay, good. So, given that we're paying less than 50 cents a minute, it would make sense that our answer is less than 20. So, given that 4 times 4 is 16 and we're messing with decimals, Andrew, $16. It actually ends up just being $16. So 20 plus $16 is 36. And then we already did part C. We already interpreted the pricing plan, so I'm not going to spend time writing that out. Okie doke. All right. Definitely a review from last year, but still something that can trip you up. Looking at intervals, increasing, decreasing, and constant intervals versus positive and negative. So looking at this first graph, along what interval, and I've got some points labeled. Can you read all those? I've got -4, 0, 0, 6, 2, 8, 5, 0, and 7, -12, just in case you couldn't read those. What interval along which would you say this is increasing, Mackenzie? Perfect. -4 to 2. Now, so that's like part one. As far as interval notation is concerned, would you be using, well, tell me about brackets and parentheses here.
They both use brackets.
No. They're both actually parentheses. Shoot. When you said there aren't they both, I was thinking you nailed it. Because is it actually increasing at -4? No, that's where the slope is 0. Is it actually increasing at the top of this hill here? No, because the slope is actually 0 right at the tippy top. Just so you know, all things increasing, decreasing, and constant, when you're talking about slopes and interval notation, they're always parentheses. So you really don't have to think about it. So 1, 2, and 3, no matter what the problem, what the context, those are always going to be parentheses. So part 2 here, interval along which it's decreasing. Aiden. Very good. Keep going. 2 to 7. Perfect. And again with that, always parentheses. And when we have two different intervals, we kind of adjoin it with that union symbol that we worked on. And then constant. There is no constant interval here. There's places where the slope is 0, but you would never write in interval notation from 2 to 2. That doesn't really make sense with interval notation. So there is no interval, there's no span of time. Only instantaneously is the slope 0. It's never like sustaining a flat line. How about positive? Along what interval or intervals is this function positive, Marissa?
-4 to 5.
-4 to 5. Talk to me about, she's correct, talk to me about brackets or parentheses.
Would I use parentheses?
Correct. Because at -4, it's not actually positive. It's right on 0. And same thing at 5. So she did a good thing there. Positive does not mean, like, not to be confused with a positive slope. Increasing means positive slope. Positive, just plain old positive, means above the x-axis. Okay? When else? She missed one other, because there's a union here. Andrew?
Negative infinity and -4.
Very good. And infinities always get parentheses, and again, this -4 is going to get a parenthesis because it is technically a 0 and not included. So with that one, it's kind of weird because you can't just say negative infinity to 5. You actually have to close each one individually at -4 because that one and only one point is not technically positive. And then negative... Oh, Mitch.
The 5 to -12.
You just committed a terrible sin.
5 to 7.
5 to 7, exactly. You really want to fight, resist the temptation to look at the y coordinates when you're doing interval notation. Tell me about parentheses and brackets here, Mitch.
Parentheses on 5 and brackets on 7.
Beautiful. Good. Because 7 is a filled in dot, and so that in and of itself, that truly is in the negatives. Good. Okay? Take a minute and do part B on your own, and then we'll touch base, see where we all stand. Aiden, did you not have homework? You can get half credit. Mm-hmm. Julia, did you have homework?
Yeah.
Joe, do I have everything? Oh, yes. There's the end. Sorry.
No, you're good.
Where's Connor?
Now you're good.
Oh, that explains it. And Mitch. I think you might have misunderstood. You just filled this in.
Oh,
You were supposed to actually, you didn't have to fill this in. You were just supposed to do that assignment. So let me give this back to you, and then if you're busy tonight, don't worry about it till, just by Wednesday. Try to get caught up with that one. Okay. Oh, who haven't I talked to yet? Bridget. What'd you have for the increasing interval?
I said that there wasn't any.
There was none?
Yeah.
Did anybody have anything different? You should have had one, Bridget. So what does increasing mean to you?
That, well, I thought that it was because, like, now the arrows are coming up.
Okay, but increasing to you should mean a positive slope. So do you see any places on this graph where there's a positive slope?
Negative infinity.
Correct. Okay. So yeah, there's no arrow going to the right there because it's not infinitely going. I use one on the left because, yes, that's going to continue forever. But anytime you're looking at increasing, decreasing, you're thinking, as I move along the graph left to right. So just because that arrow's pointing that way doesn't mean I can't still think about moving left to right. If it's going up, that means increasing. Okay? Negative infinity. Anybody have anything different other than that? That should be correct. And how about decreasing? Bailey?
Negative infinity to negative 6 and 5 to infinity.
Decreasing. So from here to here, the graph is decreasing.
Well, yeah, I think the arrow confused me.
Yeah. So you don't. We all know that arrow just means that the graph is continuing forever. So it doesn't mean that. I mean, if you're looking at the graph right to left, yes, it's going down. But when you're looking at slope, you're looking left to right. How's this graph progressing? So this is going up. So can you try that again?
Yeah, just 5 to infinity.
Very good. And then our constant slope. Joe. Very good. -2 to 5. How about our positive? Morgan.
-6, -2, and -2 to 5.
Okay, and then I'm going to ask you for parentheses or brackets.
Parentheses on -6 and -2.
Mm-hmm.
And bracket on -2 and 5.
Yes, but what are some of you thinking about that, her answer? Because I would argue that one element of it is not correct, and it's probably my own fault. Mackenzie?
Bracket next to the -2 to the -6, -2, the bracket at the end.
Say it again?
I don't know what the bracket, but I put a, like, for the -6, -2, I put a bracket.
On this one. On the -2 one.
Oh, I used the other one. Yeah.
Well, she brings up a good point, though. Bailey, what were you going to say?
Does it have to do, like, Because it's still positive after it's going, like, after the 5.
Yeah, and that's why I said maybe it's my fault, because maybe I should have given you a point here, because it's still above the x-axis after the 5 for a little ways, right? So let's just call that 6, 0. And then we would actually end that second interval at 6. But I still want to go back to something that Mackenzie I didn't honestly even think about it. And I am actually going to check with Mr. Hill on this just to be positive. But I'm pretty sure what, Andrew?
There'd be a bracket or a parenthesis on the 6.
The negative 6? Or the 6? Oh, there would be yes, now that I changed that from a 5 to a 6. Something else. Anybody else have any thoughts back to what Mackenzie was saying? Marissa? Yeah, and as I'm looking at it, even though the graph splits up, I don't know that we have to split up this interval. Because isn't it positive the entire way from negative 6 to 6? So even though it breaks up right here, if you were to say, is it positive or negative at negative 2, it's still positive. Even though it's not this one up here, because that's an empty circle, it's still positive. So I actually think that you could just say negative 6 to 6. I'm going to double check on that. That's kind of a rare situation to come up. But I'm going to say with 99% confidence that you can just write that as 1. Because it doesn't really make sense to use a parenthesis there. I know why you did, because the open circle, and we were splitting it up because the graph was split up. I get that. But the more I look at this, and I have used these same notes for 3 years, and I don't think I've ever had that thought before. So there you go. Just goes to show you. Always learning something new. That never, maybe I'm misremembering, but I don't ever remember having this conversation. But it's a good one. All right, and then lastly, the negative interval. Nate.
Negative.
Okay. Mm-hmm. Right, now that I've told you that's a 6, now we can actually complete that. Okay, good. All right. And last but not least, relative maxes versus absolute maxes, and same things with the minimums. So what would you say on A? And I'll just write it up here. What would you say, without me reteaching you, because hopefully you did this last year, what, if any, points are relative maximums on A? Sarah. Well, I'm looking for a point.
Okay.
So a relative maximum point.
2.8.
2.8, very good. How about the absolute maximum point or points, in case it happens more than once? What would you say for the absolute max? Any volunteers? Abby, can you take a guess?
Would it just be 2.8?
Is that the absolute highest point the graph ever reaches? No. The truth is I appreciate you guessing. There is no absolute maximum point, though. When something is going towards positive infinity, you can't quantify what that absolute highest point is. So there is no absolute maximum in that case. There's a relative maximum because that means relative to the points on either side of it. So relatives are typically your turnaround points, where we increase and then we start to decrease. But absolute is just the absolute highest point it gets to, and you cannot quantify that with infinity. And then how about relative minimum, Julia? Do you have any of those?
-4, 0.
Very good. And any absolute minimums? John?
7, -12.
Very good. 7, -12. Okay? And sometimes your relative minimum is your absolute minimum. That obviously happens. There's no like rule. It just kind of depends on the picture. And relative maximum here, what do you think? Sarah, we'll hit you up again.
-2, 4.
That's not actually a point on the graph, believe it or not. When it's an open circle like that, okay? So unfortunately, that would not be a relative maximum because it's not actually even a point on the graph. Anybody else want to take a stab at this? Olivia, I'm going to have you take a stab at this. 5-1 is a maximum relative to the points on the right-hand side of it, but it also has to be a maximum relative to the points directly to the left, and it's not because it's even with those. Does that make sense? So we actually do not have one here. DNE does not exist. How about absolute max? What do you think, Aiden? The absolute maximum point this reaches.
What do you,
What's tripping you up? What's making you a little bit cautious to give me an answer?
The -2 point.
Exactly. So we know it gets up to like -2.00001 and 3.99999. But again, you can get infinitely close to 4, right? 3.99999, but then you can just add 12 more nines on that. And so you also cannot quantify that. So there is no absolute maximum point, believe it or not. We know it never reaches 4, but as far as just getting slightly under 4, you can't quantify that because there's an infinite number of space, an infinite amount of space there. Our relative minimum, we also do not have one of those. And actually, we do not have an absolute minimum because of those arrows. Okay? So, pretty interesting features on that second one.